So good day everyone. Now today we're gonna learn about number conversions, arithmetic operations, and Boolean algebra. So here we have a given number in base 10. We're gonna convert this number into base 2, base 8, and base 16. So I'm gonna teach you the shortcut method of how to convert different bases of a number. Okay? Here we have a given of 30,826,674.25. In converting this number, we're gonna separate the whole number here and a decimal number. So the shortcut method is that you're just gonna write the last digit of the number here, of the whole number, that is a 4, as you can see, and then divide this number by 2. So if you divide this by 2, you'll have a result, and that result has a digit or last digit of a 7. Divide again that result by 2, and the resulting number has a last digit of an 8. So repeat the process again and again. Just copy the last digit until it is not, or the number is not divisible by 2. Okay, so here I'm just gonna write the last digits, the digits that I have come up. So we have a 4, 7, 3, 6, 3, a 6, an 8, a 4, a 2, a 6, 3, 1, 0, 0, and a 5. Okay, and then 7, 8, 9, 4, 7, 3, 1. So sorry about my writing. I hope you have a clear vision of it. So what we're gonna do with these last digit numbers, we're gonna assign zeros and ones. So assign a 0 for an even number and 1 for an odd number. So here we're gonna assign a 0 because this is even, the 4. Here we're gonna assign a 1, and so on and so forth. Assign zeros and ones. This is even, odd, this is odd, even, odd, even, odd, even, odd. Here we have 7, odd, even, this is odd, even, odd, and an odd number. So you're just gonna write the result, that is 1, 1, 1, 0, 1, 0, 1. You have a 1, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0. There. Okay. So I hope you get it. Now we're gonna convert the decimal part. So here we have a decimal of 0.25. As you can see. Okay, what we're gonna do is just multiply it by 2, and you'll get 0.5. If you multiply that again by 2, you'll get a 1.00. And if you multiply that again by 2, you'll get a result of 2.00. But 2.00 is not included in a binary number, or it is not a binary number. A binary number can only be 0 or 1. So we have results 0 and 1 here, the leftmost digits. So here we have to write 0 and the 1. As you can see, 0 and 1. So there you go. This is the result in base 2. You have to write 2 so that it is a basis, or a base that it is in base 2. So if you want to convert this into octal, you just divide this binary number into groups of 3. Okay, so here we're gonna divide it into groups of 3. We have 0, 1, 0, as you can see. 0, 1, 0. We're gonna write it here. 0, 1, 0. Put a decimal in there. This is a 0, 1. So it lacks a 1 bit. So you have to add a 0 at the right. Okay, do the same for the to the left. We have 110 here, 110, and so on and so forth. So we have 010, 000, 110, 100, 101, 110, and 001. Okay, so now what you're gonna do with these binary numbers is you'll get its corresponding decimal value. So a 001 is a 1, a 110 is a 6, a 101 is a 5, and so on and so forth. This is a 4, this is a 6, a 0, a 2, a 6, a 2, and this is a 2. So your final answer is this one, 16546, okay, 0262.2. So there, I hope you get it. That is the final answer in base 8. If you wanted to convert it again into hexadecimal, you just have to divide the given binary number into groups of 4. Okay. If you want to divide it into groups of 4, you just have to divide it into groups of 4. So we have decimal, we have 0, 1 there, and then add 2 zeros to the right. And same in the left side, we have 0010 there, and do it to the rest of the binary numbers, 1011, 4 zeros, we have 0110, 0110, 1101, and 0001. There you go. So again, you're gonna find its corresponding decimal number. Here, this is a 1, this is a D. This stands for D because our number is up to 9 only. So we're gonna assign A as a 10, B as 11, C as 12, D as 13, E as 14, and F as 15. Okay, so we have D here, we have 6, we have 6 here, this is a 0, this is a B, okay, this is a 2, and this is a 4. So the final answer would be 1D660B2.4. And this number is in base 16. If you wanted to convert back the given binary number into decimal form, you just have to multiply it to the base, or depending on the base of the corresponding position. So what I mean is that let's have it here. So 1, okay. The result a while ago is this one. So here we have a 0 and a 1. The 0 stands for 2 to the power of negative 1. The 1 stands for 2 to the power of negative 2. Okay? Here, this 0 is in a position of 0. This one is in position 1, 2, and 3, and so forth. So what you have to do, the 1 here is multiplied to 2 to the power of negative 2. That is equal to 0.25. And we have a 0 multiplied by 2 to the power of negative 1, which is a 0. And then a 0 again, multiplied to 2 to the power of 0, that is a 0. And a 1 multiplied to the 2 to the power of 1 is equal to 2. So if you do this, or to the rest of the binary numbers, you'll have different results. You'll come up with results. And what you're gonna do, you're just gonna sum up these results, and this comes back to its original form here. The same is happening to the octal and hexadecimal. So here you have a 2, that is e to the power of negative 1, and a 2, e to the power of 0 is a 2, and so on and so forth. And if you sum up these results, it comes back to its original decimal number. And the same happens with the hexadecimal also here. So 4 times 16 to the power of negative 1 is equal to 0.25. A 2 times 16 to the power of 0 is equal to 2. A b is an 11. 11 times 16 to the power of 1. Because it is in base 16, we have to multiply it to 16. Here, it is in base 8, we have to multiply it into 8. Here, it is in base 2, so we have to multiply it by 2. And the power depends on the position of that digit. Okay, so I hope you get it. So do it for the rest of the digits of the hexadecimal number here and compute the sum, and the sum will be going back to its original form, the number of the base 10 number. Okay, so now that we've learned how to convert a number into different conversion depending on the base of the number system, we're gonna do arithmetic operations. Okay, so here in arithmetic operations, we're gonna implement the ones and twos complement. So I'm gonna teach you how to use this ones and twos complement in arithmetic operations. So here we have a problem, 1,964,365 base 10 plus, okay, so it is plus minus, so we add this number here at the top, we add it here at negative 1,008,431 base 10. So here we have calculated it in advance just to have a basis of our result later on. So we have calculated the result will be 955,934 base 10. So the first thing you're gonna do, you're just gonna convert these numbers into its binary form. Okay, I hope you get it. So I've computed this in advance, so the binary number will be, so I want to suggest that you convert these numbers into binary for your practice, so you have to pause the video. Okay, so for now I'm gonna convert this into its binary form, that is 111011111, okay, 00101 0010101. That is the binary equivalent of this number at the top. And the second binary is 01111 011 000 1100101111. So these are the binary equivalents of these numbers respectively. We're gonna do, since this is a sign of a positive, this is a sign of a negative, we're gonna assign a 0 for a positive sign and a 1 for a negative sign. So here we're just gonna attach a 0 here, okay, stands for a positive sign, and here we're gonna attach 1. Okay, I hope it's clear to you because this is a negative. Okay, so the technique here is just look for a negative number, and here excuse me, and here the negative number is this one below. Okay, so this one we're gonna convert it into its ones complement. So how do we convert this into ones complement? Okay, first you're just gonna look at the binary and then copy the sign, just copy the sign. The sign here is a 1, stands for negative, and the rest of the binary, reverse it. Okay, what I mean by reverse is that a 0 will be a 1 will be a 0, just like that. Okay, so we'll reverse it. There you go. So this is the ones complement. Ones complement. If you wanted to find the twos complement, just add 1, and there you go. you have the 2's complement. 2's complement. And what you're gonna do with the 2's complement, you're just gonna add it into this number here, the positive number. So we're gonna add this one. Okay, we already know the basics of adding numbers or binaries. 1 plus 1 is a 0 with a carry 1 here, 1 0 0 1. Okay, and just add all of it. Okay, and the resulting sum will be 0 0 1 1 0 1. Okay. So for those of you who do not know, a 1 plus 1, 1 plus 1, okay, will be a 0 with a carry 1. So this becomes like that. And a 1 plus 1 here, for example, if you have like that, so your 1 plus 1 is a 0 and a carry 1. 1 plus 1 is a 0 with a carry 1. Okay, 1 plus 1 is a 0, plus 1 is a 1 there and a carry 1. So that becomes 1 1 0. Okay, so that you have a knowledge of how to add these two numbers. They're pretty large numbers, so I have to make it fast. So as you can see, there is an overflow. What you mean by overflow is that there's a excess of number in the binary digits. Okay, so this excess will be disregarded. Okay, this will be disregarded, and the final answer will be 0 0 1 1 1 0 1 0 0 1 0 1 1. Okay, 0 1 1 1 1 0. Okay, and that is in base 2. That is the final answer. Moving on with the next problem. Here we have again the same process will happen. So here we're gonna convert this binary, we're gonna convert this binary, and then add a binary digit at the leftmost depending on the sign. Okay, so here we'll have 1 0 0 1 1 0 1 1 0 0 0 1 1 0 0 0 0 1 0. Here we'll have 1 1 0 0 0 1 2 3 4 0 1 1 0. Okay, those are the binary equivalents, and here a negative sign can be seen, so we have to add 1 here, positive sign, so we have to add 0. So here the negative number is this one, so we'll have to take its 2's complement. By taking its 2's complement, just let the sign be 1 and take the reverse of the rest okay, so we'll have 1 0 1 1. And by taking the 2's complement, you'll have to add 1 there, and you'll have there you go. This is now the 2's complement, this is the 1's complement. Okay, you see this, that is not that hard. Okay, so you'll add the 2's complement to the positive number, positive binary equivalent. So when we add both of them, okay, we've done it earlier here, the first example, so I hope you get it. So the result will the this one. There we go. Notice that the result has no overflow. Unlike this one, it has an overflow. So if it has no overflow, should I say, this answer is in 2's complement form. Okay, so this will not equal to this number here that we get, or this result. So in order to have a result that is equal to its decimal, like here, or a binary result that will equal to the decimal here, we just have to reverse the procedure of getting 2's complement. Okay, so we'll minus 1, we'll minus a 1, and the result will be like that. And then take the reverse of 1's complement. Okay, let the sign be 1 because it is the sign. This is the sign right here. Okay, this becomes here. Okay, so if you compute this one, if you compute this binary here, not include this because this is the sign, this stands for a negative sign. If you compute this binary here, you'll get a decimal equivalent equal to here. So the next topic I'm going to teach you is about basic BCD operation, or binary code decimal operation. So here we have two numbers in BCD, 36543.81 BCD and 54,646.43 BCD. Okay, for me this can be regarded also as a decimal number system, but let's just regard to it as a BCD number. Okay, we'll simply add this one and we'll have a result that will equal to 91,190.24. So what we're gonna do with BCD operations here, we're gonna take the corresponding binary equivalent of each of the digits. Okay, so 83 will correspond equal to 0011. Okay, did you get it? And then next number is a 6. Okay, 0110. Just put a space in between them. Okay, and so on and so forth with a 543. A 5 is 0101. The next a 4 is 0100. A 3 is a 0011. Decimal. An 8 is 11000, and the 1 is 0001. Okay, there you go. Okay, same process goes with the second BCD number. So we have 010145. Number A4 is 0100. A6 is 0110. A 4 is again. A 6 is decimal. A 4 is 0100. And a 3 is 0011. Okay. Okay, easy. So we'll have to add these binary numbers. Okay, so a 1 plus 1 is a 0 with a carry 1. 1 plus 1 again, a 0 with a carry 1. 0. 0 plus 0 is 0. 0 becomes 1. 1. Okay, decimal. 1 plus 0 is a 1. 1 plus 1 is a 0. Carry 1. 0 carry 1. 1. 0 0. 0 carry 1. We have a 1. We have a 1. We have a 0 carry 1. 1. There you go. I hope it is clear on you. 0 plus 0 is a 0. 0 1. 0 1. Okay. And lastly, there you go. Okay. Observe the results. Observe the results. If you have observed a binary equivalent that is equal or greater than 9, you have to add a binary number of 6. Okay. So here, this is not greater or equal to 9, so we have to add 0 0 0. Here, this is greater than 9. Okay, we have to add 0110. Here, this is also greater than 9, 0, 1, 1, 0. This is not greater than 9. Okay, this is, we have to add 6 here. This one also. This just add 0. Okay, so the rule is, if the binary is greater than or equal to 9, you have to add a binary of 6. Okay, that is the last process. So just add this. You have 0 plus 0 is 0. This is 0. This is 1, 0. Okay, 0. It's 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, I hope it is clear on you. 1, 0, 1, 0, 1, 0, 1. Okay, and then we'll have 1, 0, 0, 1. Okay, there you go. So this is the result, and the last process is you're just gonna convert these groups of 4 binary numbers into its equivalent decimal. Okay, so here a 1001 is a 9, a 000 and a 1 is a 1, and again a 1. This is 1001 is a 9, 4 zeros is a 0, decimal 0010 is a 2, and 0100 is a 4. So as you can see, the result is the same with the ones in here. Okay, they are the same. Okay, so lastly, I'm gonna teach you about the Boolean algebra and its simplification. Okay, the simplification of Boolean algebra. Here we have a function. So here we have a function f. Function f is equal to a b prime dA. Okay, enclosed here, or ended by c plus c prime, or c prime, or a b prime cde, or a cde and b or b prime, or a b cde, or b c prime de, and a or a prime, or a prime b c prime de. So a plus here is an OR gate, and here a multiplication is here, so this will be an AND gate. So here we're gonna simplify it by using the distributive property. We're just gonna simply distribute this term individually to these terms. Okay, so we'll have AB prime CDE, okay, plus AB prime C prime DE here, distributing here, and the same with the remaining terms. Here we're just gonna copy AB prime CDE, copy it down like that, and here we're gonna distribute this ACDE to B plus B prime. So ACDE multiplied by B is ABCDE, plus ACDE multiplied by B prime is A B prime CDE. Here just copy. Here we also distribute, so we'll have these results here. So results in this one. Lastly, we're just gonna copy. These are all done by distributive property. Okay, by theorem 1, we're just gonna exclude those who have similar terms. Okay, what I mean is same as here. Here we have AB prime, okay, AB prime CDE. This is the same as this term, AB prime CDE. Okay, we have also AB prime CDE here. And according to theorem 1, an x or x is equal to x. So if this term ORed by this term will be the same term, and ORed by this term will be the same term. So here is a single term, AB prime CDE. Okay, here it has, I think it has no similar terms, so just copy it down. Here we have ABCDE. So here we have ABCDE. an ABCD also, so exclude the one ABCD, just copy the other one. The same happens with the ABC prime DE. Okay, just copy the AB prime CDE, A prime BC, or ABC prime DE, I'm sorry, here and here, both terms are similar. So x is equal to x. Here, this one or this one is equal to a term itself in theorem 1, according to theorem 1. And then by distributive property, we're gonna factor out again the similar term. So here we have a common term or a common literal AB prime and DE, AB prime and DE. Okay, so here is the common, we factor it out, and what's left is C or C prime. Okay, so here ABCDE will remain the same, and here we factor out the common literals BC prime DE, and what's left inside is A or A prime, these two. This is according to distributive property. And according to postulate 5, a C or C prime or an X or X prime will equal to 1. So here this will equal to 1, and this also will equal to 1. According to postulate 2, X and 1 or any literal multiplied by 1 will be that literal. So X and 1 will be an X. Okay, so here we multiply this term by 1, and this will become the same term. And this also copy, and this also. By distributive property again, we're gonna factor out the ADE because it is common in here, these two here. We factor it out and just copy this down. And according again to distributive property, we have this one can be regarded as B prime plus BC, or B prime or B and C. So according to distributive property, this is equal to B prime plus or B and B prime or C. And again, according to postulate 5, this one here will become a 1. And according to postulate 2, x ended by 1 is x. So this term ended by 1 is that term. Okay, so the final answer or the simplified form is ADE and B prime or C or BC prime D. Okay, that is the final function. Okay, in order to verify if the simplified term is right or correct, if it is right or correct, we should construct a truth table for the original and simplified expression. So here, as you can see, it has 32 outputs, okay? So here, this is the truth table for the original expression, and as you can observe, it is similar to the truth table for the simplified expression. Now, it is an exercise for you to verify also and to make the truth table for original and simplified expressions. Okay, so as you can see here, this is the logic circuit for the original expression. So it is obviously seen, sorry for the camera, can be obviously seen that this has more logic gates, okay, than the simplified expression here. Okay, you can try this creating of circuit designs in the Proteus, okay, and you'll verify also the truth table. So that's all, everyone, and I hope you've learned something, and thank you very much.